Example 1 from Work and Energy Part 2. We've got a mass attached to a spring. We pull it to the side, which is the picture that it's shown. We let it go, and it will oscillate back and forth. So here's our equilibrium position where it's labeled x equals 0. So the mass is going to move past. It's not just going to stop when it gets there. It'll move past that point and oscillate back and forth. For part A, with no friction, there's nothing taking energy out of our system, so it will just oscillate back and forth like that forever. Part B, we add in friction. It would eventually slow down and stop, but we're only interested in the motion from where it's shown here to equilibrium and how fast it's going when it gets there. So, energy conservation, we're going to have a change in kinetic and a change in potential. And for part A, that's all there is. There's no other forms of energy taking place. So if we write that out explicitly, we've got K final minus K initial, which is delta K, plus our change in potential, which is U final minus U initial, and that all equals 0. So the final kinetic energy is the kinetic energy it has at equilibrium. So we can write that as 1/2 mv squared. It started at rest, so there was no initial kinetic. The potential at the final position, at x equals 0, the spring won't be stretched or compressed, so that will also be 0. But it started with elastic potential energy in the spring. So if we group all that together, solve for v, we get the square root of k over m multiplied by our initial stretching distance. And we can see that this seems to be a reasonable answer. If our x sub I value started off larger, then it would end up moving faster as it gets back to equilibrium. If it started off smaller, v would be smaller. If x sub I started out to be 0, well then it's already at the origin with 0 speed and it would remain 0. The other terms too, if k were larger, that would be a stiffer spring. That would naturally make it be going faster because it would have stored more potential energy. If the mass were larger, that would end up giving it a slower speed because it's got more inertia. So if we go back here and look at part B, now we're adding in the coefficient of friction between the block and the surface. So we start out solving that the same way, only now, so we've got our delta K and our delta U. Now we have a change in internal energy because of that work done by friction. And so I'll make a note over here. The change in internal is equal to the magnitude of the work done by friction. Because the work done by friction is always negative because the force of friction opposes the displacement. But the change in internal energy, what friction does is takes mechanical work, turns it into heat, and that adds to the internal energy of our system. So for the first two delta terms, we have the same stuff. We're going to end up with 1/2 mv squared minus 0 plus 0 minus our initial potential. So I just omitted the zeros that were up here. And now our change in internal energy term is going to be the work done by friction, so that's the frictional force, which is mu mg. Because since it's sitting flat, the normal force is just mg, multiplied by distance that it moves, x sub I. And all of this is equal to 0. So now when we solve for v, right, so first I can get rid of these 1/2s if I multiply through by 2. I can get rid of m, I put that here. So now v is going to be all of this. So we move this to the other side, we're going to get k over m x sub I squared minus 2 mu g x sub I, all of that big square root. So we have our original term, but we're subtracting off this term, which makes sense compared to our original solution because it should be going slower if it lost some of its mechanical energy due to friction. So those are our two solutions for parts A and B to example 1.